All right, welcome everybody to our Wednesday meeting. We're very happy to have Professor Alberto Cattaneo from Zurich, University of Zurich here. He will talk to us about Poisson structures from corners of field theories. Please, Alberto.
Okay, thanks for the invitation. So we'll touch several topics out of mathematical physics and mathematics. Somehow the ultimate goal is to study quantum field theories on manifolds with boundaries and corners. I will present a particular example, which is that of a classical part of a 3+1 dimensional gravity, so I mean physical gravity, in the Coffrane formulation, also known as Palatini-Cartan formulation. So basically, this talk is based on some general work with Pavelnyov and Nikolai Reshetikhin on the BV formalism and its connection to what happens on boundaries and corners. Worked with several of my students, including Nima Moshayedi, Michele Schiavina, Konstantin Wernli, and in particular for the gravity part with Giovanni Canepa, who is my last PhD student on these topics. Okay, so let me just start with somehow an illustration of the dream of what one would like to have. So the idea is to have some field theory, some quantum field theory. We'll not tell you much about quantum field theory because in this talk we'll say more on the classical side. But this is just as a motivation. But the idea is that you have some field theory, classical or quantum, on some space-time, which now in this picture is two-dimensional, but of course it could be 3-4-dimensional. And you assume that your space-time is some manifold, which may have boundary components and also corners. So somehow the boundary itself has some extra pieces of boundary, which in this picture, the bulk is two-dimensional, the boundary components are one-dimensional, and then the corners would be the next level, would be zero-dimensional. So for example, this point here. And then what happens here is that, of course, you have different pieces of the one-dimensional boundary. So this curve, for example, this curve or this curve attached to each other through these zero-dimensional corners. So this is some of the underlying geometrical picture. And then the point is what you expect to get, or how do you expect to describe field theory out of this picture, and why are you interested in this picture? And the reason is that, use this kind of picture because then the idea that you want to glue together different manifolds with boundary along a common boundary. And actually, if you have corners, you also have the option first to attach together different pieces of boundaries together. So you do first this kind of gluing, and then you glue together the boundaries to go to the highest picture. In principle, you can, if you start in higher dimension, you might also go lower down, like codimension 1, codimension 2, codimension 3, and so on. Now, what should you expect in field theory? What kind of description should you expect? So basically, you should have some pieces of data associated to the bulk, to the corner, to the bulk, to the boundary, to the corners, and some gluing rules. So geometrically, you can glue pieces together, and you should get some structure that can also be glued in some way. So I will start with the quantum picture, which is, of course, more difficult in principle, but easier to describe because it's just linear algebra. So the idea is that to the bulk, so for me, bulk is sigma here. Let me tell you what I associate to the boundary. So to the boundary, you associate some Hilbert space. It will be the space of states of your theory. And to the bulk, you just associate an element of the space, so just some vector. Now, the idea is that now your boundary might be cut off into two pieces of boundary joined at a corner. And then the idea is that, if you glue the pieces together, so for example, you glue this piece of boundary with this piece of boundary, right? You get a boundary to which you should associate a vector space. So in my picture here, the two pieces are called sigma 1 and sigma 2 here. And they're glued together along a common corner. And so you should have a vector space associated to the glued boundary. So sigma 1 union sigma 2 along the corner. So this will be the vector space. And you should be able to produce this vector space by gluing objects associated to boundary components that have their own boundary, which is the corner. So there'll be something associated to sigma 1 and something associated to sigma 2. I keep calling them H sigma 1, H sigma 2. And well, what you expect this to happen from other reason is that these H sigma 1 and H sigma 2 are not only vector spaces, but actually are modules for some algebra. So the idea that to the corners, so you go to dimension 2, you should associate some algebra. This algebra acts on the two vector space, say from on the left, on this one, on the right, or the other way around, maybe on the right with respect to this one, and on the left with respect to this one. And then you just take the tensor product of these two vector spaces over the algebra that acts on both, and you get a new vector space. So this is the idea of how things should be glued together. And okay, so this is what you expect for several reasons. And now what happens at the classical level, which is the one I will discuss in this talk? Well, you basically you dequantize and this picture and see what you should expect at the classical level. So in classical mechanics, instead of having Hilbert spaces of states, you have symplectic manifolds. So you should expect that to a boundary component, you associate some symplectic manifold. And then you should dequantize associative algebras, and from works and deformation quantization, you can expect that the dequantization of an associative algebra should be a Poisson algebra, or actually, I think in manifolds, a Poisson manifold. I will tell you later on what a Poisson manifold is, but essentially is a manifold with an appropriate algebraic structure on its algebra functions. And then what you have to do, if you, again, you have a boundary, sigma 1 and sigma 2 joined together along a common corner C, then to sigma 1 and sigma 2, you should associate some manifolds that I will still assume to be symplectic, but they are even a bit more than symplectic, namely they are related to some Poisson manifold associated to the corner. So here the picture, so maybe let me also write it down. The picture is that you should think of M1 and M2 having common projections to PC. So this is the picture here. And now here M1 and M2 are symplectic manifold. PC is a Poisson manifold. Now I will explain later on. Symplectic manifolds are special cases of Poisson manifolds. So everything in this diagram are Poisson manifolds, and you should think of these maps to be Poisson maps. Okay, so this is the picture that somehow dequantizes the picture that you have modules over a common algebra. And then what you do here, when you do this, you just take the fiber product over these two projections. So this is what I've written here. This is some new manifold. Well, if it happens to be a manifold, assume it's a manifold. And this manifold doesn't have a nice structure directly, but it's a submanifold of the Cartesian product of M1 and M2. You can put a symplectic structure over the product. And this submanifold turns out to have to be pretty nice. It is what is called a quasotropic submanifold in symplectic geometry. This is a kind of submanifolds that have a nice reduction. So this is the underline is some reduction, some quotient, some nice quotient you can associate to this manifold. And the quotient is defined in such a way that you get a new symplectic manifold. So the final upshot is that symplectic manifold associated to the glued boundary component glued together along the corner is this procedure here. You just take the fiber product of the two symplectic manifold over the common Poisson manifold, and then you take an appropriate quotient. So this actually is a picture that appears in symplectic geometry in the work of Alan Weinstein, but fits very well with this description. Okay, so this just to give you the general dream, and then in this talk I will tell you how you could try to realize this dream in some examples. And actually, I will stop actually at the construction of this Poisson structure associated to the corner. So what has to be done is this gluing, which I will not describe here, and then the quantization, which it hasn't been done yet, apart from some sporadic examples. Okay, so now let me give you some background and some results. So something that at the moment does not seem to be directly related to this picture. So this is some other part of a background, just about affine the algebras, and then I will connect the two pictures. So
sorry, there is a question, maybe?
Yes.
Yeah, so in this first picture, that's the previous slide. Am I thinking in the right direction when I was saying that this looks kind of like a fully extended field theory where you're mapping into some sort of Morita category of Hilbert spaces?
Yes, it's related to that. Yeah, sure. I mean, you can make these very precise in topological field theories. For non-topological ones, of course, it doesn't work so nicely. But yeah, that's the idea.
Okay.
Yes. Okay, so let me recall you what an affine Lie algebra is. So we start with some finite dimensional Lie algebra G together with an invariant inner product. And then the first thing we can do is to construct a new Lie algebra, an infinite dimensional one, which I call GS sub S1, which is just maps from, say, continuous maps from S1, actually, probably, yeah, smooth maps from the circle to the Lie algebra. Okay, and what you can do is you just like extend the Lie bracket you had here pointwise. So you just take, you have two maps from S1 to G, and maybe, let me write down, you define the bracket of F and G at the point X just by first computing F of X, which is an element of the algebra, then G of X, which is also an element of the algebra, and then you just take the Lie bracket in the Lie algebra. Okay. Then there is another operation you can do once you have these two Lie algebra valued functions. Well, what you can do is, well, you want to integrate over S1. So first of all, you need to produce some one form. So, okay, you can take the differential of one or two functions, for example, G. This will give you some one form on the circle, but this will be a one form taking values in the Lie algebra. But F is a function taking values in the Lie algebra. So you can now use the pairing in the Lie algebra to get an honest one form on the circle. And then you can integrate over the circle. Okay, so you get a number. So to two Lie algebra values functions, you associate a number, which I call C of F and G. Okay. Now, this object turns out to be a cocycle for this Lie algebra. I will not tell you what a cocycle is. I will tell you what, I mean, an equivalent description, which is what is needed here. Mainly means the following. You can extend your Lie algebra by adding a one-dimensional space. So you get now, well, your infinite dimensional Lie algebra S1 plus this one-dimensional factor. And I want to make this into a new Lie algebra. So I have to define a new Lie bracket. So on a direct sum, so here F and G are Lie algebra valued functions on S1. A and B are real numbers. And I define the bracket this way. So there is one first component in this first amount here, which is just the pointwise bracket I have defined here. And then there is a second component, which is just a real value, which is the number I produced here. Okay, so, well, saying that this is a cocycle is equivalent to saying that this is a Lie bracket, namely that the Jacobi identity is satisfied. So this is the whole point. So notice that A and B disappeared on the right-hand side, which means that there are central elements for this Lie algebra. So this is what is called a central extension for your original Lie algebra. And this is an example of a affine Lie algebra. So central extension of these loop Lie algebras. So, well, they are widely studied for several reasons. And well, some of the reasons is that they are related both to Chern-Simon theory, which is a topological field theory in 3 dimensions, and to the Wess-Domino-Witten model, which is a 2-dimensional conformal field theories. Okay, I will not tell you how they are related to the Wess-Domino-Witten model. Actually, they are related through the correspondence to the Chern-Simon theory, but I will tell you how they are related to Chern-Simon theory. So namely, they are related in the sense that they correspond to the Poisson algebra I should associate to corner of Chern-Simon theory, which is a 3-dimensional theory. I will explain this correspondence later. So first of all, let me tell you how we should think of, I mean, how should we relate this affine Lie algebra to a Poisson manifold? So I don't know, should I say what a Poisson manifold is, or does everybody know it?
I think it's fine.
It's fine. Okay. So here the idea is to think of well, what is a Poisson manifold associated to this? So whenever you have a Lie algebra, say a finite dimensional Lie algebra, you can take its dual space and make this canonically into a Poisson manifold. Namely, the point that linear functions on this manifold are just element of your original Lie algebra. So you declare the Poisson bracket just to be the original Lie bracket, and then you extend it to all smooth functions just by requiring that this bracket should be a biderivation. Okay, so the idea is to do the same here. So we have this Lie algebra G hat, the extension of central extension of the loop algebra, and we want to consider its dual as a Poisson manifold. So I put this in quotation mark because now this is infinite dimensional. So first of all, I'd like to tell you what I understand as a dual and in which sense we should think of this as a Poisson manifold. So first of all, remember that G hat consisted, or actually GS1, let me understand this first. GS1 consisted of Lie algebra valued function on S1, that is Lie algebra value 0 forms. So I think of this dual just by defining it as 1 forms on S1 tensor the dual of the original finite dimensional Lie algebra. So this is my choice of the dual, and the pairing is just the canonical pairing between the dual of the algebra and the algebra itself, and the pairing of 1 forms on S1 with 0 forms on S1. Okay, so this would be Poisson manifold within a affine Poisson structure, which is defined by this Poisson structure here. So actually, the other piece of information that whenever you extend a Lie algebra, whenever you extend a Lie algebra by, do a central extension of a Lie algebra, you can define the Poisson manifold just by taking the dual of the first summand and taking an affine Lie bracket. So there will be a linear part that corresponds to the original Lie bracket and the constant part that corresponds to the cocycle. Okay, so the idea is to think of this infinite dimensional manifold as an affine Poisson manifold. Of course, since it's infinite dimensional, things do not work quite properly. So, I mean, for me in this talk, the definition of an infinite dimensional Poisson manifold like this one means that there is an appropriate subalgebra of the whole algebra of functions on which you can define a Lie bracket, which is also by derivation. So I will not have, the Poisson bracket here will not be defined for all possible functions on this infinite dimensional space, but on some nice subalgebra functions. Okay, which, okay, now this works algebraically as it is here. Okay, now the main goal of this talk is to describe a two-dimensional generalization of this. So again, this is just something like by itself, is not very difficult, but this will play a role when you want to consider corners for certain four-dimensional field theories, in particular BF theories, and even more importantly, gravity. So the two-dimensional generalization is the following. So you start again with a finite dimensional Lie algebra G, but now instead of considering a circle, you consider a closed surface gamma. Okay, so the first thing we do is again to consider maps from gamma to G, and again you can take the pointwise Lie bracket. So this is a new infinite dimensional Lie algebra. Now we have to do something new with respect to the previous case. I have to introduce some dual of this space, and again I define this dual. Actually, it's not really a dual, so I use this notation for the dual because I take the dual of the Lie algebra, but here I take 1 form. So this is not really the dual of this one. It should be 2 forms. No, I take 1 forms here. And, well, this is not the algebra in a natural way, because when I multiply 2 elements here, I would get a 2 form. But what I can do is I can define a coadjoint action of this Lie algebra on this space. Namely, when I take a Lie algebra value 0 form, I can let it act on a dual of the Lie algebra value 1 forms just by taking the coadjoint action of G on G dual and multiplying the 0 form component with the 1 form component here. Okay, so what I can do then is just take the direct sum of these two infinite dimensional spaces and regard it as a new infinite dimensional Lie algebra. Okay, so the bracket is just that of the semi-direct product here, which means that so if f and g are the algebra valued 0 forms, alpha and beta are 1 forms valued in the dual of the algebra, the bracket is defined here. In the first summand, I just take the pointwise Lie bracket, and in the second summand, I take this coadjoint action of like f on beta minus the 1 of g on alpha. Okay, so this is a new infinite dimensional algebra. And then I want to take some central extension. So I have to define a cocycle, and the cocycle is defined here. So remember here, f and g are 0 forms, alpha and beta are 1 forms. So if I take the differential of g or the differential of f, I also get a 1 form. So here I have the product of 2 1 forms, and here the product of 2 1 forms. So I get a 2 forms. Now, alpha takes values in G, G takes value in G dual, so I can use a canonical pairing between G and G dual to get an honest two form. And the same here. This is just to skew symmetrize, and I can integrate over gamma. And one can check that this is a co-cycle for this Lie algebra, or equivalently, that you can use this function to centrally extend your original Lie algebra. Okay, so now we have this more complicated situation. So yeah, F and, oh, this should be G. No. So F and G are Lie algebra value 0 forms, alpha and beta are 1 forms taking values in the dual of Lie algebra, and A and B are real numbers, and the bracket is defined here. So in the first component, so inside here, I use the bracket I defined before, and in the second component R, I just use this function. Okay, so this is a Lie algebra, is not difficult to check, and the point is that this Lie algebra is related to this field theory. So let me quickly tell you that there are some generalizations. I will not delve into it in the first one. So the first one is that instead of having just a separate closed to manifold and Lie algebra, I mean, more general situation when you have a Lie algebra bundle over your two manifolds. So in this case, instead of taking Lie algebra value or dual Lie algebra value, 0 form, 1 form, you have to take sections. Not a problem. And the only problem that when you have when you want to define this co-cycle, you will need some connection. So some connection A0, but I mean you can use that connection to make this work. I mean, but you have to choose this connection. The second generalization, which will be interesting, is the following. So suppose that your finite dimensional Lie algebra is equipped with an invariant bilinear form. Then what you can do, you can deform your original co-cycle by this other piece. So you just consider the two one forms, alpha and beta. They can both take a value in G dual, but then you use the pairing to get an honest two form, and you can integrate it. Okay, and then you just choose some parameter lambda, some real number here. Actually, for any lambda, this will be a co-cycle, and so for any lambda, you'll have a central extension of your the algebra on gamma. Okay, so it turns out that these central extensions are all related to four-dimensional BF theory, which we'll mention later on. This parameter lambda corresponds to what is called a cosmological term in those theory. Let me just tell you what is the correspondence. I will tell you BF theory later on. Essentially, it's basically they're described by this kind of equation. So the idea is the following. Again, we have to go to the dual of this Lie algebra. Right? This would be Poisson manifold. So remember, the first summand in this Lie algebra where Lie algebra value 0 forms. So for me, the dual will be 2 forms taking values in G dual, and the second summand here where 1 forms taking value in G. So for me, the dual will be again 1 form. Sorry, 1 form taking value in G dual. So for me, the dual will be again 1 forms, but now taking value in G. Now we'll call an element here A. This is a Lie algebra value 1 form. I use the letter A because I would think of it as a connection, 1 form. And we'll call this 2 form taking values in G dual as B, just because B comes after A. Now, it turns out that you think of this as a Poisson manifold. We can take a submanifold defined by this equation, the curvature of A plus lambda B equal to 0. This will be a submanifold here. And it turns out that this submanifold is a Poisson submanifold, namely you can restrict the Poisson bracket. Okay. Algebraically just means that the vanishing ideal of this inside well, the algebra function, we just take like the symmetric algebra of the dual of this, symmetric algebra of this, sorry, is an ideal. Yeah, it's a Lie ideal inside here. Okay, so this is what it means algebraically. So notice that for lambda different from 0, this is clearly a submanifold because you can just solve the equation. B is a curvature divided by lambda. So it's a graph, no problem. For lambda equal to 0, this becomes a bit singular. So it's not really a submanifold. Okay, now let me come.
Sorry, can I just ask a quick question at this point?
Yes.
You know, maybe I should know this, but I forget. So this equation, FA equals plus minus B times the scale, that is, of course, a famous equation in the theory of two-dimensional connections with values in Lie-2 algebra, which is this is known as this fake flatness condition. Is there a generalization here where B takes values in another Lie algebra, which has a homomorphism to G?
Yes.
I see.
I think this is related. I mean, there are. I mean, the generalization of BF theories where you have that. I mean, you make the generalization. Yeah, sure.
I see. And let me also quickly ask: are you going to say the gamma is still a two-dimensional surface, right?
Gamma is the close two-dimensional surface now. Yes.
But nevertheless, we are headed towards four-dimensional BF theory.
Yeah, the idea that this is a two-dimensional corner of four dimensions.
Oh, I see. Right. Okay. All right. Thanks.
Yeah, and BF theory is quasi characterized by this equation. Plus, well, another equation that for lambda different from 0 comes automatically from this one, namely that the covariant derivative of B is equal to 0. And if lambda is equal to 0, you have to impose it as a separate equation.
All right. Thanks.
Okay, how is this related to gravity? Well, first of all, you have to choose the Lie algebra appropriately. So the Lie algebra for gravity will be the Lie algebra of special orthogonal transformation for a metric with signature 3,1, if you really want to work in Minkowski space, or SO4, if you want to work with Euclidean gravity. So you have to take BF theory, the two-dimensional description of BF theory with this Lie algebra, restrict to this Poisson submanifold. Right? And then further restrict to one more submanifold. So namely, first of all, you take B different from 0, and then you require the Pfaffian of B to be 0. Okay, so the idea is that, you can identify these Lie algebras with 4x4 skew-symmetric matrices and do the dual as well. So B will be a 4x4 skew-symmetric matrix at each point, and you compute this Pfaffian. And you want this Pfaffian to be 0. And so it turns out that if you do this, the resulting Poisson submanifold describes the corners of four-dimensional gravity. Okay, so at the end, this turns out to be rather simple looking. That is, you just take BF theory, which just means doing this construction they did before, I mean this general construction here, which is pretty simple. Then you impose this constraint, and then you impose this additional constraint. So here it seems that for the gravity just comes from four-dimensional BF theory by this constraint. This happens to be the case on the corners. If you try to do the same in the bulk, it doesn't work so nicely. But it turns out that once you're in the corner, this idea works pretty well. So in the bulk, you might try to get four-dimensional gravity out of four-dimensional BF theory by putting some constraints on the B field. But I mean, the point that when you do this in the bulk, you're essentially breaking some of the symmetries that are there, so everything becomes very, very, very messy. Whereas on the two-dimensional corner, these things work pretty well. Of course, this is not the way we do it. We do not declare the Poisson manifold, the corner Poisson manifold, the gravity to be the Poisson corner manifold BF theory with this additional constraint. We have a construction of the corner Poisson manifold associated to field theories, and when we do it for gravity, we realize that it is related to BF theory this way. So it is somehow, I mean, an outcome of the construction, not the starting point. Okay, so now let me come to the second part, namely, I want to tell you how to get these Poisson corner Poisson structures. Actually, in general, what we get is something a bit more general, P infinity structure, so Poisson structure up to homotopy. And first, I will tell you something about Poisson structure, how to describe them in terms of supermanifolds, and how to describe P infinity structures in the same language, and then we will see how they appear from field theory. So first of all, okay, you know what a Poisson structure on a finite dimensional manifold M here. Eventually, we want to generalize to infinite dimensional one, so we'll cheat a bit. So we want to think rigorously now, assume that M is finite dimensional. So remember that a Poisson bracket is equivalently described by vector field. And a bivector field is the same thing as a function on this graded manifold. I take the cotangent bundle of M and I shift it by 1. So again, should I say some words about supermanifold, graded manifolds, or is this known?
Yes, maybe if you could say a quick sentence, it might help some people in the audience.
Well, actually, probably we'll focus just on this example of graded manifold. So basically, what I mean here is something very simple. So this, okay. Supermanifold, graded manifold are generalization of manifolds in the sense that you generalize the sheaf of functions of a manifold by adding a second factor in them. So basically, you consider a sheaf over your topological space, which locally is isomorphic to a tensor product of the sheaf of functions, to a sheaf of smooth functions, tensor product with some X0 algebra. Okay, so you add this extra factor. And you think of this X0 algebra as the odd part as functions over odd coordinates. So odd coordinates are coordinates that anti-commute with each other instead of commuting. Okay, and here, I mean, for simplicity, we can just take the global picture. So I think of this thing here as T star 1 of M as such a manifold, and just have to tell you what is the global, section of a sheaf. So which I will call C infinity. So this will be function of these things, and these are by definition section of the X0 algebra of the tangent bundle. Okay, so you can just stick to this definition. Okay, so a function over here will be a section here, and here I put a grading. This one here means that I think of the fiber coordinates to have degree 1, which in this description just means that I think of this as a graded algebra. So the grading is so I say that a section, so a section of degree K is a section of wedge K Tm. Okay, so a bivector field is a section of wedge 2 Tm. So is a function. Sorry, it's a function of degree K. A function of degree K on this graded manifold is a section of wedge KTM. The bivector field is a function of degree 2. Now, since this is a cotangent bundle, it turns out that it has a canonical symplectic form. You can repeat the construction you do for usual cotangent bundles. I mean, the easy way is to go to local coordinates and see what happens. So you can define the canonical Poisson bracket. And it turns out that this canonical Poisson bracket is nothing else than this Haupt-Genaue noise bracket of a section of the X0 algebra of the tangent bundle. And well, what is a Haupt-Genaue noise bracket? Well, you know the Lie bracket of vector fields. So what you can do is to extend it to multi-vector fields just by the rule that it should be graded by derivations with respect to its entries. And it turns out that this bracket on multi-vector fields is not only graded skew symmetrics, but it also satisfies a graded version of the Jacobi identity. And so it's a graded Poisson bracket over this algebra, which we think has a graded Poisson structure over this manifold. Now, a bivector field defines a Poisson structure if and only if it's a Haupt-Genaue bracket with itself is 0. So in this language, this Poisson bivector field is a function S of degree 2, which Poisson commute with itself using the canonical Poisson bracket on this cotangent bundle. Okay, so this is a description here. Okay, now what you can do is to generalize this, and instead of taking an ordinary manifold here, you can already take a graded manifold. So you can assume M to be a graded manifold, which means that, okay, it's already defined as a sheaf of functions, as I said before. So we have additional gradings and additional commutation parity rules. Now, a function S of degree 2 will be essentially, what you like by definition, a collection of multi-vector fields, pi 0, pi 1, pi 2, and so on. So here, pi k is a k vector field. And when I say that this has degree 2, I mean that the degree, the internal degree, so with respect to this grading here and the original degree grading on the manifold, so the degree of the k vector field should be 2 minus k. So in particular, it means that the bivector field will still have degree 0 as before, but now you can also have a vector field of degree 1, a function of degree 2, a trivector field of degree -1, and so on. Okay, but you still want this condition here, and so this condition now will boil down into several brackets between all these various multi-vector fields. Now, it turns out that this is related to L-infinity algebras in the following way. So what you can do, if you have k functions on your manifold, you can take their differentials and you plug them into the k vector field, and this will give you new functions. So you have this bracket with k entries. So we call it the k-RE bracket. And the fact that these multi-vector fields have these commutational relations, which I summarize in this single equation, is equivalent to saying that this is, this multi-bracket define an L-infinity structure on functions on my manifold. So if you don't know what an L-infinity structure is, it means essentially that, well, it's not just a least algebra structure. The algebra would be the case when you just have the binary bracket. Here, there is also a bracket with one entry, which in the nice case is a differential. And then there are higher bracket, which in particular tell you how the Jacobi identity is violated. Here, I might have also this pi 0, which means I can also have the operation with no argument. So this L-infinity structure will be curved, but okay, don't want to enter into these details. Now, what I call a p-infinity manifold, or means the following: it's a manifold such that on its algebra function we have an L-infinity structure consisting of multi-derivations, like here. So precisely the situation here. So a p-infinity structure on a manifold can be described by this data game. So this shifted cotangent bundle and a function of degree 2 to satisfy this equation. Now, the data I given here, a graded manifold, theta 1m, and function of degree 2 commuting with itself, is something we like to call a BF2V manifold. So actually, this should be theta 1m plus. So, well, why BF2? Well, this is just a name. Well, just remember these two here. These two here is related to the fact that it has degree 2. We will see later on that there are also BF1 manifold, BV manifold, which means that this index will be 0 and so on, which is our generalization of this. Okay, there are some generalizations of this. So the first is, instead of starting directly with the cotangent bundle shifted by 1, you can start with some graded manifold M with a symplectic form of degree 1. Okay. Now, it is a theorem that in this odd case, you have global Darboux coordinates, which means that you can always realize this graded manifold as a shifted cotangent bundle, but this is not canonical. You have to make a choice. So this more general version is related to the previous one by what I call a choice of polarization, which is a choice of symplectomorphism between your original symplectic manifold and this shifted cotangent bundle. So after this choice, you are back into this situation, and so you can define the p-infinity structure. So let me give you a very simple example to explain this. So start with the finite dimensional Lie algebra G. Take its dual as a Poisson manifold, as said before, and then take its cotangent bundle shifted by 1. So this will be my M. And I said before, over here, we will have this BF2V structure. So this function of degree 2. Okay, so what is this function of degree 2? Well, this is just a bivector field associated to the KKS Poisson structure on G dual. Okay, but now we think of this as a function S. So now on this cotangent bundle shifted by 1 of G dual, I have this function of degree 2 that commutes with itself. So explicitly, this cotangent bundle can be written as G dual direct sum G shifted by 1. Okay, this vector bundle trivializes because G star is just some Rn. Okay. And the interesting thing that I can view this as a different cotangent bundle. Instead of viewing it as a cotangent bundle shifted by 1 of G dual, I can see it as a cotangent bundle shifted by 1 of G shifted by 1, right? When this will be now G shifted by 1 will be the base, and then I have to take the dual, which will be G dual shifted by -1, and I should shift by +1, so I get back to G dual. Okay, so I can view it this way. So now, I mean, my base manifold is G shifted by 1, and by definition, functions on G shifted by 1 is just the exterior algebra of G dual. And it turns out that this function of degree 2 on the symplectic manifold M, which here in this picture was realized as a bivector field on G dual, in this other picture here is realized as a vector field on G shifted by 1. And so in the associated L infinity algebra structure, you only will have the unary operation. It is a differential over here, and this turns out to be the Chevalier-Albert differential. So as you see, this picture unifies the Poisson algebra structure on the dual of the algebra with its Chevalier-Albert differential. They turn out to be, well, the same, well, not the same, but they seem to be obtained from the same structure. This symplectic manifold of degree 1 and this function of degree 2. And, well, you obtain one or the other just by choosing different polarizations. Okay? Now, there is one further generalization, which is a bit more algebraic, and which is actually quite important because it's the one that you can use in the infinite dimensional case. So the idea is the following. So first of all, instead of thinking that you have a Poisson, a graded Poisson, a Poisson manifold, like, well, oh, sorry, right here you had right T star 1 of M as a symplectic manifold, but the only thing we used was a Poisson bracket here. So the only important thing is that this is some graded Poisson manifold. But actually, since we are only using the Poisson bracket, you might think just of having some graded Poisson algebra, which doesn't have to be the algebra functions on a symplectic Poisson manifold, as in this example. Okay, so you just start from a graded Poisson algebra. You take an element of degree 2 that Poisson commutes with itself. These are our important data. Now, the next thing here, which generalizes the polarization we had before, is the following. So remember, first we had a polarization here, which consisted in just selecting right the functions on M, I mean selecting the base M, and then just taking the basis. Functions on the basis. These were the P infinity algebra was defined. So what we do now, we just choose some splitting of the graded Poisson algebra into two summands, H and G. So H will correspond to this, and G in this example will correspond to the rest. That is proper multivector fields. And we have to put some algebraic condition here. So the first condition is that both H and G are Poisson subalgebras, which happens in this case. And the second condition is that H is abelian, namely the Poisson bracket restricted to H is 0, which happened here. Okay, and then you can define an L infinity structure on H as follows. So take elements, say take k different elements, k the elements on H, F1 up to Fk. So what you can do, you can take iterated brackets with this element S. So first the bracket between S and F1, then you take the bracket with this F2, then the bracket with this F3, and so on. So at the end, you get some element of the algebra, but you use this splitting to project it back to H. So this projection is just, P is just this projection. So this way, again, we have k-ary brackets on elements of H. Okay, and it turns out that this equation here implies that this bracket form an L infinity algebra structure on H. So now, nice thing is that this is fully algebraic, so we can do this also in the infinite dimensional space. We start from some infinite dimensional manifold M, and we would like to repeat the previous construction. The problem is that right, the functions on the cotangent bundle of our infinite dimensional space is not really a Poisson algebra, but it contains a nice Poisson algebra. And then you can do this construction here. Okay, now let me go back to my first picture, and well, how to refine the claim in that picture is that if you start from some field theory and in the BV formalism, which will not explain now, then under some some regularity conditions, you can associate to such a theory a BF2V structure on codimension 2 corners. And then by choosing a polarization, you can get a P infinity structure on corners. Okay, in some cases it will be a Poisson structure, but in general it will be a P infinity structure. Okay, and just to tell you how boundary and corner are related, the point that this structure will be related to fields of the theory, and so essentially you will have boundary fields, corner fields. You can restrict boundary fields to the corners, and dually this will give you a map from the space of boundary, sorry, not dual, yeah, map from the space of boundary fields to the space of corner fields. There will be some Poisson structure here, some symplectic structure here, and you want this to be, actually, you try to show that this is a Poisson map. Okay, so we'll not explain this part, but I will explain a bit this part here. Okay, so this construction is pretty obvious in so-called AKZ theories. So just let me tell you in a nutshell what it is. So what it is the following. You start with some finite dimensional graded manifold Y, which we will think later on as the target. So on this finite dimensional manifold, we assume that we have a symplectic structure, omega, of degree n-1, a function of degree n, which Poisson commute with itself. Okay, so this is actually what I would call a BFNV structure. So the case we considered before was the case when S has degree 2, so this was BF2V, right? Now we have the generalization in degree n. And actually, for some reasons, it's important here that the symplectic form is exact. So it will be the differential of some one form alpha. Then there is another piece of data that you have to consider. You pick some k-dimensional, closed k-dimensional manifold sigma, and you consider its cotangent bundle shifted by 1. Okay, and then you put these two data together by considering maps from this graded manifold to this graded manifold. Okay, so I will lie a bit here. What are these maps? So, I mean, if there were ordinary manifolds, you should consider maps, usual maps between them. This would be some infinite dimensional thing on which you want to put a manifold structure. Now, in the case of graded manifold, this turns out to be a bit more complicated. This is not just the space of morphisms between these graded manifolds regarded as an infinite dimensional manifold. It's really the adjoint of the Cartesian product. So you should think of this really as a linear home, I mean, and then you view it as an infinite dimensional graded manifold itself. Its degree 0 part will be the morphisms, but you will also have parts in different degree. And now, well, as Alexandrov, Kontsevich, Schwartz, and Zaboronsky showed, you can put a nice structure over this space of maps, actually a BFN-KV. So again, a structure of this kind, but with a shift in the dimension of the manifold. And the shift appears because you do transgression. Essentially, you pull back data from the target and you integrate over the k-dimensional manifold, and this produces this shift. So in particular, this means that over this graded manifold of maps, you will have a symplectic form of degree n-k-1, a function of degree n-k, and the function commutes with itself. Now, usually you take the case when k is equal to n to describe a B theory in the bulk, but now we want to do the corner version, so we take k to be equal to n-2. So the result is that on this mapping space, we will have a function S of degree 2, which is precisely the BF2V structure. And to this, you can associate a P infinity structure. So the outcome of this construction will be the following. If you have a bulk theory, which actually is a topological theory defined by the AKZ construction, then when you go to the corner, you get a P infinity algebra structure just by doing this construction here. Okay. This looks like a trick because this AKZ structure works right this way for all dimensions. The reason why this is really related to what you want to get out of field theory is that I mean, there is another way of getting the result really by transgressions from boundary to from bulk to boundary, from boundary to corner, and so on, which is essentially the correct way, conceptual way of keeping track of boundaries whenever you use a Stokes theorem. And in the case of AKZ theory, it boils down to this nice construction. In the case of gravity, you cannot do this because it's not an AKZ theory, so you really have to go through the proper construction. Okay, so now what I can tell you is that the examples I gave at the beginning are related to certain certain field theories. So, for example, the case of the affinity algebra is related to Chern-Simon theory. So this is a three-dimensional theory which can be formulated in the AKZ formalism. The second example, the one where I use closed surfaces, was related to four-dimensional BF theory, which is also an AKZ theory. But the case of coframe for the gravity is not an AKZ theory, so we have to go through a different construction. So let me quickly go through example of this AKZ construction. So the first example is BF theory in 2 dimensions. So this means that our source will be 0 dimensional, which means that this mapping space is by definition just a target Y. Okay, so in this case, Y is just the cotangent bundle shifted by 1 of my target, and my target here will be, I mean, okay, I choose this as to be the target, right? Which we already saw is a BF2V manifold. So sigma is a dimension of 0, so the mapping space is Y itself. So we consider this structure on the mapping space. And again, by choosing the polarization, this goes back to the example I described before, either the Poisson structure on the dual of the algebra or the Chevalier algebra differential. Chern-Simon theory, I will go very quickly here, is the one where you choose as a target G shifted by 1. And the source, again, will be 2-dimensional. If you do this AKZ structure, you end up with this construction here. I will not describe it, but once you choose polarization, you get this affine the algebra. So for me, it's more important to describe 4-dimensional BF theory. So let me do it very quickly. So the result of this AKZ construction on the surface, sigma, is the following. So in addition to the fields we had before, A and B, remember in our description, A was a 1-form taking value in the Lie algebra, and B was a 2-form taking values in the dual Lie algebra. Now we have additional PCC, B dagger, phi, and tau. So on this side, everything takes values in the Lie algebra, and well, A was a 1-form, but now we had C, which is a 0-form, and B dagger, which is a 2-form. And I add additional degree for the graded manifold. And on this side, everything takes values in the dual of the algebra, and to B, which was a 2-form, I also assume I'd add a 1-form tau and a 0-form phi. And I mean, when formally I write the symplectic form this way, this simply means that somehow the momentum associated to B is C, the momentum associated to A is tau, and B dagger and phi are one the momentum of the other. And the function of degree 2 can be written here by this expression. And if there is a cosmological term, you add this other term here. So it's just defined in terms of an integral. You don't have to pay too much attention. Now, the interesting thing that you can now choose polarization. There is one natural polarization where as a basis, you put all the fields of non-positive degree. So these are A, B, and B dagger. So notice that A degree 0, B a degree 0, and B dagger a degree -1. So this is something natural. Let me see. Yeah, I want to consider this. So this description gives you back the algebra I described at the beginning. So the idea that if you go through the details, the trick is to think of the momenta of the fields here to be derivatives with respect to their corresponding coordinate, and think of this S as a bivector field, and then you just let it act on local functionals, and you recover precisely the algebra. Actually, it turns out to be a P-infinity algebra, but this is P-infinity algebra just as the operation of degree 2, just a bracket, which is actually in this case a strictly V bracket, and the differential. And you can interpret the differential just as a resolution of some ideal, which corresponds just to putting these constraints. So this is really why BF4 is related to what I described at the beginning. Okay, so with this polarization, we get back what I described at the beginning. There is another polarization which is more interesting for us. This is the one where on the base, you take the fields B, tau, and phi. So here, so the fields that take values in the dual of the Lie algebra. So if you repeat the construction here, now we'll get, again, a bivector field and the vector fields. So again, you get, well, the L-infinity algebra will just be a differential graded Lie algebra. So this here. And actually, I will restrict my action on a very simple function, so local linear functionals of the three fields. So if you apply the construction to this, actually, well, there will be a function, I mean, a bracket with no argument, which is just given by this expression. There will be the bracket with differential 1, which you should understand as a differential, which simply map this functional j into the function m, where you just change the parameter by applying the covariant derivative. Similarly, this m is mapped to k by applying the covariant derivative to beta, and this k is mapped to 0. And then you can compute the brackets, and you just get this algebraic structure. So, I mean, this is just a computation you can make. Okay, and the point that this will be related to gravity. Now, well, let me very quickly that I'm using two different polarizations. So is there a relation between polarization? Well, yes. What we expect in general, and in some cases it is proved, is that like the two structures corresponding to different polarization should be, in an appropriate sense, Morita equivalent. And I mean, if you think of this in field theory, the idea is that you have the two structures associated to two corners, and you just add one dimension by taking a cylinder, and then you try to, well, basically the cylinder in the middle is, I mean, the cylinder is the thing that should produce a Morita equivalence between the two corner structures. Okay, now let me very quickly tell you what happens in gravity. So, I mean, we'll not go into details, but just to mention what this thing is. So, the Palatini-Cartan formulation or coframe formulation of four-dimensional gravity is the one where instead of giving as a dynamical field a metric, I mean, pseudo-Riemannian metric on your manifold M, instead at each point you give an orthonormal frame. Okay, and I mean, you give a frame which you declare to be orthonormal, right? And then you reconstruct the metric out of it. Okay, so this E will be the coframe. The point, of course, I mean, given the coframe, you're giving more data, right? You have to mod out about orthogonal transformation. And for this reason, you have to also add a connection into the picture. So this Palatini-Cartan version of gravity has two fields. One is the coframe, the other one is a connection, an orthogonal connection. And basically, you can write down an action, this form, this way. I will not go into details. I mean, you can discuss this later on. So this is not a BF theory, it's something not even a KZ theory. It's some action you can consider. It turns out to be equivalent to gravity in the sense that if you take the critical point of this action, you get the Euler-Lagrange equations, and you take the space of solutions modulo the symmetries of this theory, this is the same as the spatial solution to the Euler Lagrange equation of gravity, Einstein-Hilbert gravity, modulo diffeomorphisms. Okay, so in this sense, the two theories are classically equivalent. Now, what you can do, you can apply a construction we have to go from the four-dimensional bulk to the boundary, and then from the three-dimensional boundary to the corner to construct the, a P-infinity structure. So it turns out that you have these functionals on the corner fields. I will not tell you what the corner fields are, but I have this functional to which I give cleverly the same name as to the ones we had in BF theory. And it turns out that they basically describe the same algebra. So in this sense, the P-infinity structure of gravity is the same as the P-infinity structure of a four-dimensional BF theory. We explicitly construct this algebra, we see that the algebras are the same. Of course, this depends on the choice of polarization for four-dimensional BF theory and on the choice of polarization for four-dimensional gravity. But okay, the idea that different polarization should correspond. Okay, so I think I can stop here. So this was basically one of my first slides, and now the idea that there is a construction for this. Okay, so I mean, we can also discuss more details afterwards, but probably I should stop here.
All right, yeah, thank you very much. Let's thank Alberto for this nice talk. Very good. Are there any questions?
I have
Gregory?
one. Yeah, so you're telling us BF on 2 dimensions is related to the induced structure of gravity in 4D on corners.
No, BF in 4 dimensions. BF in 4 dimensions. So the corner structure of BF theory in 4 dimensions is essentially the same as the corner structure of gravity in 4 dimensions. So both theories are in 4 dimensions, but they go to 2-dimensional corners.
I see. So how about 3D? So once you restrict to 3D or boundaries,
yes,
there is a relation to BF again.
But that also works in the bulk. 3-dimensional gravity in the Cofrain formulation is already a BF theory.
Exactly.
Already in the bulk.
In the boundaries, right? Not in the corners only, I suppose.
Already in the bulk. So in 3 dimension, gravity and BF theory are already the same in the bulk.
Yeah. So
and
I mean,
you can go to boundary and corners and remain the same.
Yeah, but if you start in 4D and then restrict to the boundary.
No,
right?
If you start in 4D, they're different in the bulk, they're different on the boundary, but they finally agree on the corners.
I see.
I mean, one reason that you immediately see they could not be the same in the bulk is that BF theory is topological, which means not only that it is invariant under diffeomorphism as gravity, but also that there's no local degrees of freedom.
Sure.
Whereas gravity has local degrees of freedom, so they cannot be the same.
Sure.
But once you go to the corner, this works.
Can I ask something? Could you maybe amplify the physical consequences of 2 theories having the same corner algebra? Like, what is it, for instance, about actual gravity that we can compute with BF theory due to the fact they coincide on corners? Can one say this?
Well, one thing is that actually just look at this algebra. So we have these, I mean, one idea is that suppose I want to glue boundaries together along a corner. So as say in the quantum picture. So what I have to do is to quantize this Poisson structure and get modules, right? Okay. So the idea from this point of view is that, I mean, since these are essentially dual of Lie algebras, this thing is even easier. Somehow I should essentially find representations of this Lie algebra. This would be the quantization of the dual as a Poisson manifold. In this case, boils down, in the case of the dual of Lie algebra, it boils down to computing, I mean, representations of the Lie algebra. So each representation or each module of the Lie algebra will be an allowed space of states for the boundary whenever the boundary happens to have a corner. Okay. And then I can do the gluing along the corner just by taking this tensor product over the Lie algebra. Now, this tells you that somehow the space of states on the boundary for 4-dimensional BF theory and 4-dimensional gravity are related because they are modules for related constructions. So what is the relation? Is that, well, first I start from this Lie algebra. Maybe let me go back here. Okay. So, so I start, yeah, from this Lie algebra I presented here. Okay, and I should first look. So here, the one with the central extension. So first, I should look for representation of this Lie algebra. Okay, then this is not BF theory, because I told you that BF theory corresponds to this Poisson submanifold. Okay, but algebraically, this turns out to be very simple. Algebraically, this corresponds just to a quadratic Casimir of this Lie algebra. So this means that I only have to look for those representations on which this quadratic Casimir is 0. So it just means that of all the representation of this Lie algebra, there will be a subset of representations which correspond to 4-dimensional BF theory. And then when I want to go to gravity, I have to impose these further constraints, and this turns out also to be a quadratic Casimir. So this means that I just have to select my representation better. So the final upshot for this is just that the spaces of states for 4-dimensional gravity are also spaces of states for 4-dimensional BF theory. The only difference that 4-dimensional BF theory has more possible spaces of states than gravity. So in that sense, it's more difficult. So this is the point. Now, the interesting mathematical questions, and that's what I would like someone to be able to do, is just start here, find representations of this infinite-dimensional Lie algebra. Okay, so in the other case I presented, like the one of a fine Lie algebra, of course, is widely studied, right? People know basically everything about representations of the defined Lie algebra. I mean, and well, essentially this is what, like in physics, goes under the name of vertex operator algebras, right? And here the point is like, well, can one find a good representation theory for this for this infinite-dimensional Lie algebra? So notice that one trick you do in the previous case, that's one, is what you do is that basically you take Fourier modes of these maps. Okay, so then this Lie algebra and its central extension is just filtration of the algebras over the Fourier modes. Okay, and that's how you basically you study them, and you study the representation theory. The point that in principle you can do the same here, because once you have your gamma, right, you can look for some appropriate basis of functions. So the simplest case are when gamma is a torus, and then you really have like Fourier modes in the two directions, or when gamma is a sphere, and then you can take harmonic harmonic functions.
Yes.
And so again, you can get a filtration of these and try to see whether these has a good enough properties to do an appropriate representation theory. Actually, the only exercise we did was the case when the original algebra G is a billion and gamma is a torus. Then you can write things very, very explicitly. And this already turns out to be quite intricate, but doable. And I mean, the difference is that if you do the same in 1 dimension less, right, you do this construction for G a billion, well, it turns out that this part is still a billion. And well, when you take the central extension, essentially this turns out to be essentially a collection of Heisenberg Lie algebras. So you know how to quantize, I mean, find the representation very easily. Actually, yeah, 1-dimensional, yeah, Heisenberg Lie algebras. And here things becomes a bit more complicated because Fourier modes into the two different directions interact with each other. So it's not just, again, a collection of Heisenberg algebras. I mean, they're coupled to each other. Okay, so maybe one message I try to give to everybody, especially my background, that it would be interesting to study. I mean, you can forget of the rest. You can just stick the 2D generalization, this infinite dimensional Lie algebra, what is representation theory of these infinite dimensional Lie algebras?
You mean as a general question? A general open question?
I mean, this is just
Yeah.
like, can't forget of physics. This is, well, an interesting mathematical question. This is an infinite dimensional Lie algebra, which has very nice properties, and can one define a reasonable representation theory?
I see. I see.
And of course,
Interesting.
the outcome that this will give you, I mean, information for four-dimensional Beer theory and even for four-dimensional gravity.
Right. And by the way, if I understand well, maybe just to amplify for the audience, so your grand goal here is to actually have quantum gravity, if I understand well, as what people call an extended field theory, right? To find out
Yes,
all coordinates.
Yeah, this is not quantum yet, it's just classical, but we get one classical piece, which should have a nice quantization. So that should be already something. And actually, if you can do the whole construction here, in principle, you would be able to construct spaces of states for four-dimensional gravity. So you could go to the boundary of four-dimensional gravity. And then only if you can do that, the whole quantization is probably not much more, because well, there is no evolution in gravity. So at the end, actually knowing the spaces of states would probably be already knowing almost everything.
I see. So maybe a good analogy is to the modular functor for Chern-Simons theory, right? Which also captures everything concerning the states, nothing about the evolution, but it's thought to essentially define the theory, right?
Yeah, maybe one could get the analog of modular functor for four-dimensional gravity, not only for.
Right. It seems you're saying for gravity, one would have to do the modular functor at least one extended, right? It has to at least go one codimension further up, right? To see the corners.
No, because you only consider the boundary and corners. I mean, already for Chern-Simons, right? Well, it depends. I mean, take the modular functor. I mean, that's already like two-dimensional.
Exactly. So the modular functor for Chern-Simons is just in codimension one.
Yes, you see dimension 2 and dimension 1. Well, you also see the dimension 1 in the modular functor. That's like the algebra. I think the point what has been misleading that, I mean, not misleading, somehow not immediately clear, is that, I mean, you do this construction for three-dimensional field theory. So you end up in codimension 2 circles. I mean, these are boundaries of two manifolds. This turns out to be actually related to West-Lumino-Witten, which is conformal. And so the upshot is that it doesn't really matter, right, how large this circle is or how far away it is. So basically, we have an equivalent description where instead of taking two manifolds with boundaries, you just take punctured two manifolds.
Yes.
And that's basically why you forget the corner.
Right, I see.
It's two-dimensional. You don't have to go one-dimensional because you have punctures.
Right.
And well, in the next picture here would be two manifolds, actually three manifolds instead of two manifolds. And well, there is a picture where you only consider punctures. And this is the one where you would allow boundaries only to be two spheres. That there is a generalization. So you can't forget of the corner. You say that you have three manifolds with punctures, and you try to generalize the modular functor there. Of course, the theory is richer because we could have boundaries that are not just two spheres, but actually tori or higher genus. So there is more structures in the punctures than just being punctures.
Okay, I see. Right, good. So maybe if there are no further questions, then maybe let's thank Alberto again for the very nice, interesting talk. It was very nice. Thanks. And maybe Gregory has to hit the button.
Yes.